By flying a kite in a thunderstorm, Benjamin Franklin was able to demonstrate that clouds carry an electrostatic charge. The fine wire connected to the kite conducted electrons to Franklin below. Franklin hypothesized that the charge moving through the conductor was positive. Electrons had not yet been discovered. If we were to repeat his experiment, but create a gap in the wire and insert a light bulb in that gap, the bulb would light up briefly as charge flows from the cloud along the wire to the ground. As a source of continuous charge flow, clouds are not only unreliable, they're dangerous. Therefore, safer more with a conductor and attach a charge or current. As are neutralized, nothing further would happen. For a continuous flow of charge, we need a source like a flashlight battery. A chemical reaction inside the battery or dry cell is its secret to success. This reaction causes the outside zinc layer to become negatively charged, and it causes the graphite rod in the middle to acquire a positive charge. We call these two charged parts electrodes. If we use a conducting wire to connect the negative zinc electrode to the positive graphite electrode, electrons will flow from the zinc to the graphite. As electrons are removed from the zinc by the conductor, the chemical reaction inside the cell transfers more electrons to the zinc. Similarly, at the graphite rod, the chemical reaction constantly removes electrons from the rod. Thus, it is possible to create and sustain a flow of charge for a long period of time. Current electricity is the name given to this continuous flow of charge. Normally, the negative electrode is not connected directly to the positive electrode. A device to utilize the current, such as a light bulb, is connected to the wire as well. The flow of charge through the bulb causes it to light up. What you see here is a simple circuit. A circuit is a complete path or loop around which electrical charge flows continuously. It consists of a source of electrical energy, a battery in this case, a conductor such as these connecting wires, and a load such as a light bulb, which uses the energy provided by the source. If a gap is introduced at any point in the circuit, the flow of charge stops immediately. As the charge flows from the cell, the chemical energy inside the cell is transformed into electrical energy. The light bulb in turn transforms electrical energy into light and heat. This circuit is said to illustrate direct current because the electrons continually flow in the same direction. The electricity supplied to your home is not direct current. If we could observe the electrons in the wire, we would see them vibrating back and forth. Alternating current is what we call this flow of charge, because the electrons periodically change direction. In this program, however, you will see only direct current circuits. The dry cell is not the only source of direct current. The solar cell converts light energy to electricity, and the thermocouple converts heat energy to electricity. In each case, there is a negative electrode and a positive electrode. We use this symbol to represent a direct current source, such as a single cell. A circuit in which a light bulb is connected to a single cell would look like this. How does a light bulb utilize the flow of charge? Perhaps you think it consumes electrons. Well, that wouldn't be correct. The wire functions like a pipe full of water. If 1 cupful of water is added at one end, 1 cupful of water will run out the other end. Similarly, for each electron that enters the bulb, an electron is forced out the other end. Since there is only one path in this circuit, the number of electrons passing a specific point X in the circuit within a specific interval of time must equal the number of electrons passing point Y within the same period of time. The word current is used to denote this rate of charge flow. It is given the symbol I and is an important characteristic of a circuit. In the modern metric system, the unit for current is defined in terms of the magnetic field it produces. In this program, however, we will define the unit for current in a more traditional way that is easier to visualize. Current is defined as the amount of charge that passes a specific point divided by the time it takes to do so. This equation is usually abbreviated to look like this. But how do we express the amount of charge? Well, we might try to count the number of electrons that pass a specific point in a specific time. But electrons are so tiny that incredibly large numbers of them pass a given point in a short time. Counting electrons would be as ridiculous as trying to buy sugar by the grain. For this reason, instead of considering individual electrons, we consider groups of electrons, which we call coulombs. 1 coulomb is equal to a group containing 6.25 times 10 to the power of 18 electrons. It's difficult to visualize a group of electrons, so instead, let's have this critter represent 1 coulomb of charge. And instead of picturing our circuit like this, we can visualize it like this. Now we can calculate current by dividing the charge in coulombs by the time in seconds. Coulombs per second are called amperes. If in our circuit 5 coulombs pass by point X in 2 seconds, we can calculate the current by dividing the charge of 5 coulombs by the time 2 seconds to give us 2.5 amperes. Perhaps now we have enough information to help our stranded parachutist. The reason he isn't getting a shock is that he isn't part of a complete circuit. If the situation changes, he'll soon be in big trouble.